this course, structural design of high-rise structures. And I'll share my screen so that we look at the course content. Where is this? Yeah. Application window, high-rise. Okay, so this is what we are meant to cover this semester. We are meant to discuss the design philosophy and design criteria for tall buildings. We're meant to cover the philosophy and design criteria for tall buildings. We are meant to discuss the design concepts for framed, shear wall, tubular, and coupled shear wall structures. I am thinking we will do justice to this and this. We will mention this in passing. We could also mention this in passing. In fact, the shear walls, for all practical purposes, you would find that coupling occurs, and I will demonstrate. I will highlight to you what that is and the kind of considerations that one would need to take. Maybe I'll even open for you a real life project. You see the issues that go with the coupling and what happens. Then we are meant to also cover considerations, or we say we'll cover this. This one, considerations of lateral loads. Considerations of lateral loads. These are wind and seismic. Basically, we will dig into this significantly. These two, we will try and make a good discussion of them in this course. Structural analysis and design of typical tall buildings. So we will do that most definitely, and computer applications to the analysis of tall buildings. I intend that we also will discuss that. These two last ones, traditionally I would combine them, so that's what I will do this semester. We will combine this. We'll combine those. And there is also usually an overlap between this one and this one. You know, you cannot talk tall buildings without talking these shear walls, tubular, coupled structures, because these are the structural systems that go into the design of tall buildings. This is a design course, and therefore its assessment will be that of a design course. Today is 20th. Let's put today's date here. Today is 20th of September 2023. Okay. Sawa. Now, I want us to agree at the start on how we will go about this one, this last topic. And the times I've taught this cause this kind of content here and elsewhere is that I prefer that we do this using a semester project. So you do a project as coursework. You do a project as coursework. Of course, this being a design unit, we will do before I come to that coursework. We'll do. Let me call it what? Semester project. Most probably, I will award 45% for that one. We will do a CAT, a timed CAT. We will do one time CAT. Most probably, this will carry 15%, or let's make them a bit closer to each other. We can do 40 and 20, and then we'll do a semester exam that we also do 40%, so that it's total 100%. You notice that therefore 60% will be on the coursework for this course. Now I am here on this project, and that's what I want to talk about, how we will go about the computer applications. Now, it is possible for me to just come here into one session and open a software or two and show you what they can do and show you their limitations and things like that. But that really does not constitute training. Training means you actually pick the software and learn it. Okay? So on this very first lecture, I want us to agree that you will, on this one, choose a software that you like. 2, get hold of some architectural drawing for building in the range of let's say 18 even to about say 22 stories tall, preferably with 1 or 2 basements. One or more basements. Let me say 1 or more basements. My gadget is hanging up. One or more basements. One or more basements. Why I'm mentioning this at the start of this unit or this course is that I want us, as we discuss these items 1 to 4, we will be implementing them step by step on a real life project. And as we implement them step by step, so we discuss something, you go and implement on this semester project. And as we do that, you will also be doing that using this software that you will have chosen, the software of your choice, and other tools of doing calculations like maybe Excel spreadsheets or what. So I will take you through step by step. So at the end of the course, we will say, so this is the situation when you started, this is how you have wound up, this is the content that you have been able to learn, so that when you go out into the field, you have a starting point. We will not by any means teach you everything that you need to know to be able to design tall structures, but in this course, the intention is to start you off. You will agree with me at the end of this unit that the content is, even as it just focuses on tall buildings, the content is still very wide. It's too wide to be covered within the content of one unit. But this course, if we do justice to it, should be able to start you off, so that when you now graduate and go out into the field, you have a starting point. Those who will find this kind of area interesting, then you know you can fully go into that and become the experts that build for us the tall buildings. Okay. I prefer to run this class the way I've run the other classes before. I know I've had the privilege of teaching you some other courses before, and I like to continue in the same manner, that preferably we meet online. I think it's a lot easier because you are able to log in from your home. I'm also able to log in from wherever location I am, and we are able to make discussions. So I prefer that we continue in this manner if you are agreeable. If absolutely you feel that we need to try something else, please, through your class rep, you let me know, and we will give that other style a trial. I have taught this course, I think now this could be the third time I've taught it successfully online. I think it's possible to instruct effectively online if the performance of the other groups is anything to go by. Those who went ahead of you were able to learn. And again, I will repeat here, please, I will be introducing to you a lot of concepts that maybe might be new to you. If I'm saying something that you do not understand, please stop us at that point. Just switch on your mic. We are very few. I mean, we look maybe 20, 28, 29. Even if we were 50, please switch on your mic and say, please, excuse me, can I have a question, or I disagree with this theory. Please, if you think you want to disagree with anything that I'm teaching, please, this is what we want. We want you guys to question the theories that we are teaching you, so that in the questioning, maybe we can make those theories better, and we can become a better world by teaching others how to do things better. So please feel free to engage as much as possible. I prefer, because this is now an application course, really, it's a design course. We are tying the analysis of structures, which you have done several units, the strength of materials, which you have done several units, the material science, which you have done probably several units. And now we are trying to tie everything to say, now can we put together all this science that we know into providing a solution, which is now tall structures. Okay, so please, at any point, feel free to just stop us and let's hear you out. Now, with that, I want to immediately delve into the first item of this content, which is philosophy and design criteria of tall buildings. And I want to change it a bit to say philosophy and design criteria of tall structures. Let's start from there. Instead of just buildings, let's say structures. So we make it broader. So philosophy and design criteria. Sorry, bad writing. Design criteria of tall structures. So was it yesterday we were talking about low-rise structures? So today we are starting on a discussion on tall structures. So what do you understand by tall structures? Ladies and gentlemen, when somebody says tall structures, what comes into your mind? This is an open question for all of us to respond to. When somebody says tall structures, what comes into mind? And the more we interact, the more interesting the session becomes. So we want to discuss in this course tall structures. What do you understand by tall structures? And as we said before, your answer does not need to be correct. It's a university. There is freedom of...
Okay, according to me,
Elijah, yes, Elijah.
what I understand with the tall structures are those structures. If you are talking about buildings, then
Yes.
those buildings with more than 5 stories going upward and carries more lateral loading than the low-rise buildings.
Actually, I think you're right in that thought. That when we start talking tall structures, it's not just about the height, but we now start getting concerned about lateral loads. The key word, what this gentleman has told us, is that now we can no longer ignore lateral loads on this structure. The structure is tall enough such that wind becomes significant and earthquake becomes significant. This basically, in a very broad way, encompasses what we would consider tall structures. Okay. Anybody else would like to say anything there before we move on? But I think Elijah has basically captured our thoughts on that. So tall structures would include, or may include, so right here in our notes, pick the correct pen. Tall structures may include buildings, which is the common one that we know. Okay, so the town is full of very tall buildings. Okay. Nowadays, in fact, if you're building in town, if you do anything that is not in the range of tall buildings, you're basically wasting land, because the cost of land is much higher than the cost of doing a slab to cover that land. So it makes sense to just build more slabs and to create, as it were, more artificial land going upwards. So buildings is one of them. There's masts. Okay, telecommunication masts, power line pylons. Those qualify to be tall structures. Then there's silos. I'll give you stories about some silos I looked at some time back. Very interesting silos. The regions of this country where we plant maize, for example, or other types of grain, we store those in these silos. Those who know Eastlands, near Donholm, there are some silos there. Okay, and many other parts of the country. If you go, especially the places where they store grain, where they store grain, cereals in bulk, they have silos. Cement manufacturers also have silos for storing cement and things like that. So silos qualify to be tall structures. Of course, we have watchtowers. Some bridges qualify to be tall structures, especially the ones that we do cable stayed or suspension bridges, because of the towers. They're very tall. The ones that are holding the cables, that are holding the deck. So these qualify easily to be tall structures, and they are actually prone to be affected by lateral loads significantly, as you will see slightly later. The main consideration for design of tall structures, the main consideration for the design of tall structures is lateral loads. That is wind and earthquake, sorry, earthquake. And I will take you back to this, your course content, and show you something. So most definitely, as we are looking at the lateral loads and how they are determined, we will also do the analysis that follows it on this your project. On this your project. Okay. And these systems will look at them in this your project. So this course content really ties up nicely. You cannot discuss one topic in isolation with the other one. This is how I look at this course content. I think it's a really good course content, well thought out. Okay, so the main criteria is lateral loads. I did mention in the other session where we were introducing the low-rise structures. I did mention galloping gutty. I don't know how many have got a chance to go and look at those videos. Anybody here who's checked them out? Or you were just watching music videos online and getting entertained? Anybody took time to check this video out? I actually mentioned 2 videos that I think are important for that class and mainly for this class. Okay, ladies and gentlemen, please, I'm repeating, go check out those videos. They're important for this content that we're doing, and they are very interesting. Okay. So, on this thought of the lateral loads, as the building becomes taller, the lateral loads increasingly become more important than the gravity loads. Let me even write that down as a note for you. As the building, or just structure in general, becomes taller, the lateral loads become more and more, it's a gradual process, more and more critical than gravity loads. And laterally, this properly designed tall structures become more and more stronger with increase in height. Okay, so I'll give you an example. Our neighbor here, in the university, our neighbor here is the Cooperative Bank building, the bell bottom. We all know it. So some years back, there used to be a shorter building next to it. It was called Ufundi Co-op. Okay. So there was the Cooperative Bank. It was there. Cooperative Bank building, which we fondly call or refer to as the bell bottom, is there. So you got the Cooperative Bank building. Maybe it's something like that. It's a bell bottom. Okay. It's a bit split. There's actually a coupling there, which we'll talk about. The two walls are the two shear walls. We'll keep referring to this building because it's next door here. And next to it, there was a smaller building, I think 4 stories or something. This, I think, is 25. There was a shorter building here, used to be called Ufundi Corp. Okay. So I think it was 1998, if I can remember properly. Some terrorists came and they wanted to bring down this bell bottom. They wanted to set a bomb to bring down the bell bottom. And the idea was that they were coming to bring a truck, or bringing a truck and driving it into the basement of the Ufundi Corp here. Explosives, eh? Okay, this is the version that I'm bought to. There's some theories, whenever something big like that happens, is all manner of theories. But I think the thinking of these guys, because what they did is they brought a truck, and as they were driving it into the basement of this building, they exploded some bomb, eh? And the idea, I think what they thought was that the shockwave would be big enough to topple this Ufundi Corp. Topple Ufundi Corp. No. Topple it. And if that had worked, the damage would have been astronomical. Astronomical. All the buildings here, all the way to Harambee Avenue, would have probably been flattened if that had happened. So when they exploded this bomb, what happened is that Ufundi Corp was completely flattened. Became a pile of rubble, 4-story or 5-story building, I can't remember properly. Flattened completely, became a pile of rubble, as in you could not find nothing from that building. What happened to the bell bottom? Structurally, nothing. No damage at all. They checked it. The structure was absolutely intact. The only thing that happened to it was the glass facade was blown away. The glass facade was blown away due to that shockwave from the bomb. But the building, intact. As a first example, what I'm trying to illustrate to you in real life is that when tall buildings are properly designed for lateral loads, they become extremely strong. So that's the first example. Let me give you another example now that we are starting this course, just to jog your minds up, just to generate some bit of interest. Around that era, the terrorists also did an attack on the Twin Towers in the US. Twin Towers in the US. Very tall buildings. Okay? I think these were about 110 stories, if I can remember properly. For you to put up a building that tall, lateral loads are so massive that it is next to impossible to generate any human-generated force that could topple those buildings or break those buildings. So what happened is that the terrorists, instead of putting a bomb here, because these buildings were done out of steel, structural steel. They brought an aircraft here with fuel, crashed it a few levels from the top. The fuel burnt. After a while, the steel became plastic. These few floors fell through the floor-to-floor height of the floor where the craft had gone in. And the falling weight of the few floors above caused the progressive collapse of these towers all the way to the ground. Very, very clever way of bringing very devastating attacks to some established nation. These guys, they knew for certain that this cannot work. This, you bring a bomb down here, probably you just shatter the glass the way it happened on the bell bottom. It's not possible. It's very difficult. You need, I don't know what kind of bombs. Check out, ladies and gentlemen. So this was the Twin Tower. Let me tell you the other one that you need to check out. Check out the building that a fellow called Timothy McVeigh tried to bring down. It was devastating, but check out the story. It's also online. All these illustrate that when we have a tall building and it's properly designed to carry the wind load and the earthquake load, they become extremely, extremely strong and powerful, that very strong that you cannot really topple it. So the how to calculate these forces and the how to design for these forces is what we want to discuss in this course. Okay? Is what we want to discuss in this course. Now, to start us off, I want us to talk about, so what is it that makes these tall buildings that strong? We have agreed that these tall buildings, if they're properly designed to take the lateral loads for their heights, they become extremely, extremely strong against any lateral push. So we want to ask ourselves, and maybe try to answer this question in this unit: what makes the tall buildings that strong? What makes these tall buildings that strong? So I'll write that as a question, and then we will try to answer it. We still have a lot of time. We can answer. So let me write this. So what makes these tall buildings that strong laterally? And to answer that question, I want us to look at structural forms and systems for buildings generally and for tall buildings. Forms and systems for buildings generally and for tall buildings. Okay. There's a way we arrange structural members in a building to make it stiff in the lateral direction. This is what we want to talk about under this small subtopic. So the most basic structural form that I want to mention is something that we call the load-bearing structures. The most basic structural form that we should first mention is what we call load-bearing structures. Very good. Load-bearing structures. Okay. These kind of structures, they transfer loads to the ground purely through masonry walls. This type of structure transfers loads to the ground purely through masonry walls. Okay, that's the first thing. So if it's a building with, say, slabs or a roof or something, the weight of those slabs and the weight of the whatever we are putting on those slabs, whether it's people, furniture, machines, or what, and the weight of the roof is transferred to the ground using or through masonry walls. Okay, I know you guys most probably you have been taken through a course in masonry design, so you know what this would refer to. There is a limit. It's important to note that there is a limit to the number of stories that you can put up, to the number of stories that can be built using this type of structure. And this limit is basically put or generated from considerations of lateral loads. We might not go into a lot of details, the why, but it's important at this point that you bear in mind that when you're doing masonry structures, there's a limit to the number of floors that you can do. Most design standards for earthquake loading, or what is referred generally to as seismic loading, they give guidance to say, for this region where there is a lot of earthquakes, you can only do this number of floors. For this region where the earthquakes are a bit lighter, you can do maybe slightly taller structures. Here in Kenya, we have an old earthquake standard, which I will introduce to you maybe in the coming sessions. We have an old earthquake code, and I think it generally limits the height to which we can do buildings on masonry to, I think, about 4 stories or 5. So I will just put this here as an example, 4 stories. Okay. We will come back to this later on, and you'll understand why there's that limit. So if you have to go beyond this number of stories, this limitation, and ladies and gentlemen, allow me to digress a bit. You remember that when we were introducing low-rise structures, we said that the limit is around here, around 4 stories, 5 stories, thereabout, depending on whichever standard you're using and whichever region you're designing to, which we will talk about to some bit of detail later. A few years ago, in a town at the coast, the Kenyan coast, there was an enterprising gentleman. I think he was an Asian. He decided to build using coral blocks. Those who've been to Mombasa and those places in the coast, you know that the masonry that is used there in the Kenyan coast is coral block. It's white. That's what we use for masonry there. Now, coral block is very weak. It's a very weak stone. You can actually, remove it with your hand like this. If you do like that, it just breaks, and it's very weak stone. Generally, when you are doing a structural wall using masonry, there are minimum requirements for strength of that masonry. I'm sure this one you were taken through to some detail when you studied or when you are taught design of masonry structures. So this gentleman decided to use coral rock, which is does not qualify as structural masonry block. It doesn't. If you test it, it is nowhere near the strength that our standards require for masonry block. This guy decided to build, I think he had gotten to 5 floors and he was now doing the 5th floor using this coral block masonry without any columns on that building. And for sure, it was a disaster in waiting. Fortunately, the authorities got hold of him and they stopped the building. I think later on they had to redo the building and maybe put on columns and change it to a frame structure. Change it to a frame structure, which is what we will discuss as the next structural system that is important for you as you consider tall buildings to know. So eventually he changed. But if he was to do this, and for example, we were to get a tremor, there was a danger that the building would just crumble, like a deck of cards. Okay, so if you have to do taller than what you are allowed for load-bearing masonry walls, then you could consider to do what we call a frame structure. This one consists of beams and columns. Pitch transfer, loading from the building to the ground. Frame structure. This is the commonest type of structure that we see around, like the U block where we have offices and we have classrooms and laboratories and everything, is a frame structure. It consists of beams and columns. So you have a slab that sits on beams, the beams are carried on columns, the columns transfer the loading to the foundation. So it's a frame structure. It's a frame structure. Generally, how the frame structure carries lateral loads. Let me just illustrate with a simple sketch here, or simple sketches. Consider these 2 simple sketches of a frame. Let's assume we have a building here. The same frame of a building. Let's draw it again here. And we have same frame. Let us load this first frame with gravity loads. Gravity loads. It's first frame. And this other frame, let's load it with lateral loads. Okay. So gravity loads, we know they are applied going downwards. It will be something like that. Some loading there on that beam, on that beam, on that beam, again on that beam, like that. These are gravity loads. I'm using a light pen so that then we can sketch the member forces that would occur. So courtesy of those gravity loads, we would get this kind of bending moment diagrams. So on the beams, we would have this kind of bending moment diagrams. The beams, which you have done in your analysis of structures, you know that you would have, for UDL, you'd have a parabolic bending moment diagram like that. These bending moments, the out of balance bending moments, like here this corner we have an out of balance moment. That out of balance moment would be carried in the column in that manner. So we'd have bending moments in the columns in that manner. Again, this would be from your analysis of structures. If somebody is interested in how you would analyze this kind of a frame easily using something we call the subframe analysis, you can consult a book by Mosley and Bunge. Mosley and Bunge, very, very good book, very simplified. Okay, so then depending on where the out of balance moments would be inside there in the internal columns, you would have things like that maybe. So you have some form of bending moment diagrams. This is gravity loads. If the frame was to be loaded by lateral loads, so we have calculated either some earthquake force, which we will do later on, or if we've calculated, say, wind load, then the moment generated on the frame would look something like that. Now, this I'm sketching for you, but once we model whatever building you will have chosen, and we load it and analyze it in whatever software you'll have chosen, this is the kind of output you will get from that software in terms of member forces. Okay, then of course you'd have forces in the columns, bending moments in the columns in that manner. Okay, bending moments in the columns in that manner. Why am I sketching these figures for you? I want to demonstrate to you that a frame structure is actually able to resist both gravity loads and lateral loads. It's able to generate a resistance. So you push a frame structure this way, it will try to push back by an equal and opposite force if the force that is trying to push it is within its a load carrying capacity. We will see a bit of detail of this later on in the discussion in this course. But generally, then if we were designing a frame structure to carry lateral loads, then we would do this analysis, and then, for example, that corner there, let me pick a color that I've not used. Yes, this corner here, we would add this moment to this moment here. Would add design for the sum. Okay, we will look at that a bit better later on. So that is the second type of structural form or structural system that we can use. And now, moving away from the load-bearing structures, we are seeing that if we were to move to a frame structure for some height of building, it makes economic sense to just have beams and columns to carry the lateral loads. okay, for some height of building. Again, this one might not be very well defined by a line because it depends on many other factors that we will see later on. Beyond this frame structure, if we had to do a taller building that the frame alone cannot resist lateral loads, then we would consider to work with a breast framed structure. So the third one that we need to mention, and maybe I need to number these so that we look a little bit more organized. Okay, so let's number these so that we look like we are a bit more organized. So that is 1. This is 2. So the third one that would increase slightly the capacity to be able to carry lateral loads is what we'd call a breast frame structure. This one, let me give a small this definition here. A breast frame structure, or just a breast frame is one that is provided with a lateral load-bearing element. This element can either be a shear wall, this lateral load bearing element can either be a shear wall, for reinforced or for concrete structures generally, or some cross bracings for steel structures. So this is what I am referring to. So consider these 2 slightly taller frames. That's a bad line. Consider these 2 slightly taller frames. Okay, so these frames have got many floors. When you have a tall frame that is made out of reinforced concrete mainly, you can have a solid reinforced concrete wall running all the way from the foundation to the top of the building. This wall, and we will discuss later, has a good stiffening effect and has a tendency to carry the majority of the lateral load on that building. And that's what is referred to as a shear wall. If this building was made out of structural steel, then we would have one bay or more that are braced that way with some cross bracings. You'd have one bay that is braced that way with some cross bracings. I'll say cross bracings etc because there's a whole array of types of bracings that you can use in a structural steel building to brace it against sway, against the lateral loads and lateral deformations. There's one building I visited here in Upper Hill that is actually made out of structural steel, and when you stand on any floor, on the windows you can see the huge, heavy structural steel sections that are bracing the building, and it's a bit ugly. It's a bit ugly. You know, architects would love to have their windows there. Now, when you do bracings like that, then you start having a need to hide them, and because they are heavy structural elements, you know, they're those structural steel, you know, UBs or UCs or something that are heavy. You realize that then it's difficult to want to hide them, so they become obvious. But secondly, also they become an obstruction such that you cannot have clear view as would have been desired. There are ways of trying to hide them and to change the style a bit, or what, you know, you could do bracings, for example, in that manner, called the A bracing. Do them in that manner, so that then you can have space for the window, but it's still a hassle or something. So this would be done for structural steel structures mainly. This would be done for concrete structures. Sometimes in some buildings you find a combination of these has been done. So right here it's possible to also do a combination of these. Okay, so now when a building does not have lateral load resisting elements, either the shear walls or the bracings, whichever way, Y bracings, K bracings, A bracings, cross bracings, etc., then we say that frame structure is unbraced. We say it's unbraced. When we have a frame structure which has got some designated lateral load bearing elements like shear walls or bracings, then we say it's a braced frame structure. We say it's a braced frame structure. A good example of these shear walls that you can see easily is on the bell bottom. Just our neighbor here. If you look at the building on the sides, the shorter sides, it's solid wall from top to bottom, the whole 25 stories and into the basement, into the foundation. This is a solid wall all the way down. That's a shear wall. University Way, there's some tall buildings there. Ambank House, I think this building where they have the anniversary towers, etc. The shear walls are obvious. You just see them from outside. And you walk in town, you find any of the tall buildings has got this solid reinforced concrete wall all the way from the foundation through the basement to the top. This is a shear wall. It's a lateral load resisting element, and it's put there to carry the shear walls. And I will demonstrate to you how the building is able to transfer almost 100% of the shear of the lateral load onto this shear wall. I'll make an attempt. Maybe for this level of discussion, it might not make a lot of sense, but I will make an attempt. The easiest example of these bracings is, we see the commonest is in elevated water tanks, water tank towers. Steel. So you see, it's this tower where then we'll put the press panel steel tank at the top. We'll discuss about tanks in the low-rise building, in the low-rise unit. But this tower, this structural steel tower, it's always braced like this, and that bracing is to stiffen it in the lateral direction so that it doesn't sway too much. So those cross bracings are the stiffening element in there, and the same principle, same thought is applied also for buildings. So if you're doing a tall building and it's structural steel, you do this. The combined system, this was adopted in the US. They changed their, I'm told, they changed their standards after the Twin Towers. After September 11th, they came back and said, if we had a concrete core, would these buildings have collapsed in 30 minutes? And the answer is a decisive no. During the investigations, the structural engineers asked themselves, if we had a concrete core in these buildings, would they have still collapsed in 30 minutes, 40 minutes? And the answer is a definitive no. Most probably they would have stayed for much longer, given a lot more time for people to be evacuated, and a lot of lives would have been saved. So they changed their standards, I'm told. I've not read their standards, but I'm told they incorporated the need that if you're doing a tall building, definitely it will be out of structural steel, but you have to have a reinforced concrete core. Why a reinforced concrete core? Because when you have a reinforced concrete element, you can control the fire resistance by playing with the cover, a concrete cover to reinforcement from your reinforced concrete design. Okay? The concrete cover is determined by two things: the environment, degree of exposure, and the fire resistance that you want. So you can say, I want 5 hours fire resistance. You just need then to find that you'll find that you need a thicker concrete cover. And if these buildings had been provided with a good solid concrete core, the thought is that maybe they would have stayed a bit longer and people would have had more time to evacuate. Maybe not everybody, but a big number of people would have been saved. Anyway, these are stories. There are many stories like this online. There are many conspiracy theories that have been floated because of that, because it was a huge event. It was a major event. I leave it to you, ladies and gentlemen, to go and watch whatever experts are saying and to make your own decision which theory you buy more to eat or what. But I'm fully bought to this theory that actually they burnt some of this. They burnt this. Go online and check the videos. The aircraft crashed. The fire was there for about 20, 30, 40 minutes. I can't remember exactly. Enough to hit the steel for that level, which then just, became plastic. Then the floors above fell, and the falling impact of the few floors above was enough to break the floor immediately below, and consistently, then the building just collapsed all the way to the ground. They also say, for your interest, that Osama was a civil engineer trained by the Americans. Go read on the story of Osama bin Laden and how they were contractors, they were builders, they were trained by the Americans. Go read those stories. They are interesting ones for guys like you who are becoming civil engineers. We are about 10 minutes to finish this unit, our time. I still have two structural systems that I want to discuss, but I think we can pick these up in the next session and discuss them, and then we go now into the details of the forces that we need to calculate, wind and earthquake. In the meantime, remember, I have asked you, I've given you the first assignment. Go decide two things. Decide what software you want to work with. Then we will discuss tomorrow, or the day we will meet again for this course. We'll discuss. I prefer, ladies and gentlemen, that you agree amongst yourselves that we will work with one software. It is a lot easier. Why? Because if you work with it and you get stuck, you can ask somebody within the class that maybe they know what to do with the whatever step that you're trying to do, with whatever error you're getting or whatever problem you're getting with that software. I also prefer that let's divide ourselves into some groups. So let's say we are approximately 30 in this class. Let's divide ourselves into 5 groups of 6 persons each. 5 groups of 6 persons each. Please, if the class rep could get me the names of each group members, 5 groups of 6 persons each. So each group, try and find something in terms of in the form of an architectural drawing that you would like to give a try to design. I am specifically asking for something in the range of 18 to 22 stories. If you want to take it to 25 stories, you get a 25 stories, even more interesting, the better. Then what else? So find these. If we get more diverse design of buildings, the better. We will learn better. We will see more problems with these buildings, and we'll be able to pick more interesting things as a class, not just as a group who has this building or this other one. Assist each other, please. If for example, you have a friend who is doing architecture who can get hold of some 1 or 2 bunches of drawings for buildings, assist the other group to also have something to present. I will be asking that we will be having a few minutes for you to show us what you're doing. I don't know. Let's have that number of groups so that everybody is involved. If we make the groups big, usually people don't work. Only a few work, and the others are just joyriding and they don't learn. So I want everybody to be involved. So find that, agree on whatever software you want to work with. There's a whole array of them. I have my preferences, which I will not tell you now. You guys just ask around, go to YouTube, check out what other builders are saying about good structural design software. Decide on that so that when we meet next time, let's have an answer on that, and let's have some sketches from for these architectural buildings that we can give an attempt to design. So thank you very much. I want to allow you, if somebody has a question or a comment, please you could ask. Yes, Nixon, your hand is up. Please go ahead. Sorry, Nixon, you need to speak up.
Can you hear me?
Ongeza volume bana.
Can you hear me now?
Yes.
Can you hear me now?
Yes. Go ahead. We can hear you now.
Yes. Oh, I was asking, does the school provide some of the softwares for design of educational purposes?
Very good question. I'm made to understand that there's a software that the university did subscribe to. I have not looked at it myself. I've not seen it. I am leaving it to you guys. Whatever software you want to work with. This is why I'm not saying go pick this one or go pick the other one. Sawa sawa, Nixon. Okay.
Yeah.
Okay, then let's have Sean Miner. Please go ahead, Sean.
Okay, it is to answer Nixon.
Yes, please.
Some of the softwares do have the student option. You just have to prove you're a student, like offering your ID card or something like that.
Thank you, Sean. So guys, you can be talking to Sean if maybe you get stuck with some of these things. Any other query or any other thought? Great. So thank you. Have a good afternoon. No, still morning. Have a good morning, and we meet again in the next session. Thank you.